Welcome to our lesson on geometric series. Today we're going to be looking at how a geometric series can go one of two ways. Let's take a look at our first two examples and just examine those two ways. In problem number 1 here, we see that we have a series saying 1 plus 2 plus 4 plus 8 and so on and so on. What we're going to do is find the sum of the first n terms, and then we will find after n terms, let's just do it more specifically with 20 terms, 100 terms, 1,000 terms, all the way to infinity terms. As you take a look at our series, you'll notice that to get from 1 to 2, from 2 to 4, from 4 to 8, you're always doing the same thing. You're always multiplying by 2. So because you're always multiplying by 2, you're adding all these numbers up. We know that what we're dealing with here is a geometric series. Okay? And recall from our earlier lesson that if we know it's a geometric series, we can go ahead and create its formula S sub n. Okay? So S sub n is equal to our first term being 1, and then we multiply that by 1 minus r to the n power. What's our r value? That's the common ratio. Our common ratio in this case is going to be the value of 2. So 1 minus 2 to the power of n all over 1 minus r. Our r value, the ratio again, is 2. So that's what S of n is going to look like. Now let's clean it up a little bit. It does look a little bit messy. So we're going to say that S of n is equal to 1 times 1 minus 2 to the n power all over 1 minus 2 gives us negative 1. And technically this negative 1, because it is just a numerical value on the denominator, we can actually bring that together, right? 1 over negative 1. And that's going to give you a value of negative 1 minus 2 to the n power, like that. Okay, so we'll leave it like that. And let's go ahead and use this formula and find the specific term numbers. So let's go on to B. So we have 20 terms. So we're going to say S sub 20, the 20 terms, is going to equal to, we just plug into our formula that we found in A, negative times 1 minus 2 to the 20th power. Okay, so let's go ahead and calculate that in our calculator here. So we're going to do negative 1 minus 2 to the 20th power. And we get a value of, let me move this over a little bit. There we go. We get a value of 1,048,575. Okay? All right, so that's our value of B. Wow, that is a large number. Let's see what happens as we go on to C. Okay? For C, what we're looking for is the 100 terms. So we want to find the sum of 100 terms. And so we can just go ahead and plug that into our formula again. Remember that in A, we found that S sub n, depending on what n is, gives us negative 1 minus 2 to the n power. So negative 1 minus 2 to the, in this case, 100th power, like that. Okay, so I'm just going to go ahead and go back to my formula and change that 20 into 100. And that's an even larger number, right? 1.267 times 10 to the 30th power. We're not going to write that entire number out. That's way too large. What you basically see here is that these numbers are getting larger and larger and larger. Let's do 1,000 terms. S sub 1,000 is negative 1 minus 2 to the 1,000 power. So in my calculator, I'm just going to add another 0 here. And this value is going to give us 1.071 times 10 to the 301st power, an even larger number. Okay, so you can expect to see that as you go to E, S sub infinity is going to equal negative 1 minus 2 to the infinity power. And this just gets so infinitely large. These numbers are getting larger and larger and larger that this is basically going to infinity. Okay? So that's how we can tackle problem number 1, letter A here, or number 1 here. Okay? Let's go on to number 2. Now there is a typo here. this actually is not a series that works out unless we do a little bit of a modification. I'm going to change this into 3 plus 1 plus 1/3 plus 1/9 plus ... Okay, so change up that first equation, or that first problem there, and now we can actually get this to work. Okay, because as you can see, as you go from 3 to 1, 1 to 1/3, 1/3 to 1/9, this actually works out now, right? What are you always doing to it? Hopefully you're saying you're always multiplying by a value of 1/3 each time. And so because we are now multiplying by a value of 1/3 each time, again, just like in our previous problem, we know that the multiplication is telling us this is a geometric, and then because we're adding these values up, we know it's going to be a series. Okay, so it's a geometric series, meaning to address our question, to address our question for letter A, what we're trying to find is that S sub n. Okay, and S sub n is, since it's a geometric series, we know it's equal to the first term being 3 times, and then we, in our formula, we have 1 minus the ratio. What's our R value? That's the 1/3. So 1 minus 1/3 to the power of n, in parentheses, all over 1 minus r, the r value being, again, 1/3. So our formula looks like that. Again, just like in number 1, let's clean it up. It looks a little bit messy right now. So we have 3 times 1 minus 1/3 to the power of n, all over 1 minus 1/3 is 2/3. Okay, let's clean it up a little bit more. So S sub n is equal to, we have the 2/3 on the bottom, so if we're dividing by 2/3, it's like multiplying by its reciprocal. So when we combine, let me do this in different colors here, 3 divided by 2/3, that's like saying 3 times 3 over 2, or that's going to give us 9 over 2. So we have 9 over 2 times 1 minus 1/3 to the power of n. Okay? All right, so from here we have our formula. That's part A. And then we can use that formula to answer B, C, D, and E. Okay, so let's go ahead and find the 20 terms now. So S sub 20 is equal to 9 over 2 times 1 minus 1/3 to the 20th power. Okay, so let's go ahead and enter that into our calculator. So we have 9 divided by 2. And then we are going to multiply that by 1 minus 1 divided by 3. And that is taken to the power of 20. Okay, and we get a value, S sub 20 is equal to 4.49999, like that. Okay. All right, now let's go on to C. Oh my goodness. C, we are looking for 100 terms. So S sub 100 is 9 over 2 times 1 minus 1/3 to the 100th power. Let's see what that's equal to. That's a, let's see, change the 20 into 100. Oh, look at that. We get a value of 4.5. Okay, let's see what happens for part D as we go to S sub 1,000 now. So in my 100, I'm going to just change that to 1,000. Huh, nothing has changed. My answer is again 4.5. Well, what do you think is happening as we go to part E of S sub infinity? Do you think anything's going to change? I can add a bunch of zeros here, and look, my value still stays the same. It's still going to be a value of 4.5. So our answer was, you can see, going from 4.49999, and then it just kept going to 4.5, 4.5, 4.5. So it kind of centered around that value of 4.5. Okay. So let's look at the differences between number 1 and number 2. And let's address the question that we see here. Why does one infinite geometric series converge to a limit? Why does it go to a number? Right? In number 1, it was not going to a number. We were going to infinity. But for number 2, we were actually going to a number, 4.5. But the other did not, right? Number 1 did not go to a number. It went to infinity. Okay, if we look at the formulas, we always use the same formula, right? S sub n is equal to t sub 1 times 1 minus r to the n over 1 minus r. But why is it that one went to an actual number while the other one went to infinity? What's the difference between them? It can't be the starting number. The starting number shouldn't change anything. But if you look at those formulas, hopefully what you're seeing here is that the one big difference among them is that one had a ratio of multiplying by 2, whereas the other had a ratio of multiplying by 1/3. Okay, so tying in what we did last week, if you remember the worksheet that we were practicing, you had a lot of examples where you saw that the common ratio affected what happened to the number. So basically, as we look at those formulas, now we can figure out when does a series converge and when does it diverge. Okay, and let's address that. When does it converge? When does it go to a number? It went to a number when the ratio was a proper fraction, right? It was basically what we can say is that the ratio converges. Oops, not the ratio. The series converges when its ratio is less than 1. Actually, let's make it as its absolute value of the ratio is less than 1. Okay? On the flip end, the series diverges, or in other words, it goes to infinity when its ratio, its absolute value of the ratio, is a value that's greater than 1. Okay? So we have those two cases. Say that value of 2 definitely greater than 1. We saw that it diverged to infinity. And when that ratio was smaller than 1, right, 1/3 is smaller than 1, then it converged. Okay? So putting those things together, what we can now say is based on that ratio, a geometric series will converge. And because if we recall the formula being t sub 1 times 1 minus r to the n power over 1 minus r, because the ratio will be a value less than 1, remember from our worksheet from the other day that if a value is smaller than 1 and you take that to the infinity power, this number keeps getting smaller and smaller and smaller until, poof, it goes away to 0. This is basically going to go to 0. And that's why when you find that the ratio is smaller than 1, then you have a new formula where you have t sub 1 times 1 is on the top, but then you minus 0. It's not even there, over 1 minus r. This is our formula for basically a geometric series that converges. Okay, a geometric series that converges gives you this formula that you see there. Okay, that's what happens when r is less than 1. If you find that the r value is greater than 1 or even equal to 1, then again, based off of the formula that we've talked about, t sub 1 times 1 minus r to the n over 1 minus r, then that must mean that this number, let's say it's bigger than 1, let's say it's a value of 2 to the power of infinity, this number is going to get larger. And because it gets larger, this gets bigger and bigger and bigger, and this, well, it relatively stays pretty small, right? So because this number gets bigger and bigger and bigger, this entire thing is going to infinity, and therefore it diverges. Okay, so if you end up seeing that the ratio is greater than 1, there's not really like a formula per se to this. You just use the same formula, but you just know that it's divergent. It just goes to infinity. So there's really not much to it. You don't have to write a formula because every formula will give you infinity anyway. Okay? All right, let's go on to the next page. Let's take a look at a couple of cases and let's figure out, even before we even start, do we know if it converges or diverges? Okay? Let's take a look at our first case here. How do we get from term to term? Notice, pay special attention to the sign that's changing. It looks like I'm going from positive 1 to negative half, to positive 4 to negative 1/8. So how am I getting from term to term? Well, in order to get those positive and negatives, that means I have to also multiply by some kind of negative value, right? Like say negative half. If I multiply by negative half times negative half is going to give us a positive 1/4, right? A positive 1/4 times a negative 1/2 is going to give us a negative 1/8. So it looks like what we're trying to say here is that the ratio is always going to be multiplying by a value of negative 1/2. Okay, so because of that, what we can say then, oh my gosh, sorry. I keep getting email or texts about Boba Day. There's Boba Day this week. Going back to number 3 though, when the common ratio is negative 1/2, we can say that the formula then is the S value is equal to the first term, which is 1, times 1 over 1 minus r, our r value being negative half. Okay, because we know that the absolute value of its ratio, negative half, is less than 1, so therefore we know that this is going to converge. Because it converges, we must be able to find its sum. Okay, so let's go ahead and find its sum. We have already plugged it into the formula. Now we just need to simplify this. So we're going to get 1 times 1 over, and then 1 plus half is going to get us a value of 1.5, or 3 over 2. And what we're saying is 1 over 3 over 2, that's the same as 2/3. So all of that, this entire series is going to add up to give us a value of 2/3. Okay? Let's take a look at our next case. We have 1 plus 0.1 plus 0.01, and so on and so on. Well, how do we get from term to term? We have to multiply by 0.1, I believe, right? 0.1 times 0.1 will give us another 0.01. Okay, so we're always multiplying by 0.1. What do we know about this? Well, the absolute value of this value, 0.1, the absolute value of the ratio is less than 1. So therefore, we know that this is going to converge. Because it converges, we can just use our formula saying our geometric series, this S, is equal to the first term, which is 1, right? Our first term is 1, multiplied by 1 over 1 minus r, the r value being 0.1. Keep in mind, we technically didn't need to have this 0.1 to the power of n because we know that 0.1 to the power of n is going to go to 0 anyway. Okay, so from this we can just solve. So 1 minus 0.1, what's that going to give us? 0.9, right? Or 9/10. So what we're saying is 1 times 1 over 9/10, or that's the same as 10 over 9 when you flip it. Okay, so that's going to add up to 10 over 9. All right, let's take a look at our next case. Number 5. 1 plus 1.1 plus 1.21. What are we doing here every time? Looks like to get from 1 to 1.1, we are multiplying by 1.1. 1.1 times 1.1 is going to give us 1.21, right? So what we know here is that the ratio is a value of 1.1. What do we know about 1.1? Well, 1.1 is definitely a value greater than 1, and therefore we know that this is going to diverge. Because it diverges, we really shouldn't be adding this. We know what it goes to. Divergent problems go to infinity. We know this is going to go to infinity. Okay? You can even test it out. You can say 1 plus 1.1 plus 1.21, right? Plus, keep on going, 1.3331 plus 1.464, right? This can keep going on and on and on. Notice how this number is getting larger and larger and larger. We went from 1, now we're all the way to 6, right? Then we're going to go to 7 and 8. It's just getting larger and larger. So this is going to be a divergent problem. We say it goes to infinity. Okay? All right, so that's how we tackle geometric series, whether they are convergent or divergent. You just want to look at the common ratio. All right, number 6. Well, this is different. Notice how our problem says 1 plus 3x plus 9x squared. And so in this problem here, what you notice is that there's a variable. because there's a variable, I don't know if this is a convergent problem or divergent problem. It depends on what x is. So because I don't know what it is, in this question it's asking us to find the interval of convergence. What that means is if it were convergent, what could the x values be? That's what this question is asking us for. We don't know if it's convergent or divergent, right? But if it were convergent, then what could x be? That's what this question is asking us, okay? So we know that based on this series, because we're going 1 plus 3x plus 9x squared, we definitely know for a fact that to get from term to term, you're always multiplying by something. What are you multiplying by? Well, hopefully what you're saying is to get from 1 to 3x, I need to multiply by 3x. 3x times 3x is going to give us 9x squared. So it looks like we're always multiplying by 3x, telling us that we have a ratio that's equal to 3x. Now, one thing you want to remember is that in order for something to be convergent, what we want to say is that the absolute value of r is less than 1. Well, that means that what we want is the absolute value of 3x to be less than 1. That's really what we want to get at. So if we want the absolute value of 3x to be less than 1, keep in mind, go back to your Algebra 1 or Algebra 2 skills. If you have an absolute value with an inequality, what you're saying is either 3x is less than 1, or what you're saying is that 3x is greater than negative 1 as well. Okay, so you want to set both of those problems up and then be able to solve for the different values of x. In this case here, the first case, we see that x can be less than 1/3. Or the other case that we have is x is greater than negative 1/3. Okay, so you can have either one of these situations. Okay, go. No. So because of this,
Daddy,
what?
The Saturn has a ring.
Saturn has a ring? Yeah, you're right. Okay.
Saturn has a ring.
Oh my gosh. Okay, so from here, let's plug in values. We know that x is less than 1/3, so here's 1/3, right? We can have it here. It can be less than 1/3, or x can be greater than negative 1/3. So we have it here as well, okay? All right, so what we're saying then is that x is in between 1/3 and negative 1/3. That's our, and you can see here that this is our interval of convergence. As long as x is in between these values, you have a series that is going to converge, okay? If you're outside these values, then it's going to be a divergent problem. So that's how x is playing a role in this series, okay? All right, so let's go on to B. Find the sum in terms of x. Well, since we know that the ratio is equal to 3x, and we know that if it is going to give us a sum, we know it's going to be convergent, the convergent series formula gives us s, which is equal to the first term. What's our first term? 1 times 1/1 minus our ratio. What's our ratio? 3x. Like that. Okay? And that's basically it. There's really nothing else you can do with this. That's going to be our sum because we don't know what that x value is. It's a range of values. Okay? All right, let's go on to our last problem here. Number 7. Find the first 3 terms of an infinite geometric sequence with a sum of 16 and a common ratio of -1/2. Well, if we know it is an infinite geometric sequence, right, and we know it has a sum of 16, that's telling us that this is a convergent problem. It's a convergent geometric series, and we know that a convergent geometric series is in the form of s equals term 1 times 1 over 1 minus r, right? So from that, we know that we have a common ratio of negative half. So I'm just going to go ahead and plug that into my formula here. T sub 1 times 1 over 1 minus negative half. Let's see, what else do we know? We don't know the first term. We don't even know the first three terms. But what we do know is that the sum is 16. Oh, well, the sum of the entire series is 16. That's going to be our S value. And look at that. We only have one more thing left to solve. We really just have t to solve for, right? So let's go ahead and do that. We get 16 equals t sub 1 times 1 over 1 plus half, or that's the same as 3 halves. And then since we are bringing that 3 halves over to the other, or what we can do is say 16 equals t sub 1. Since this is 1 divided by 3 halves, that's the same thing as multiplying by 2/3. And then from there, if you solve for t sub 1, multiply by 3, divide by 2, we will get a t sub 1 value of 24, right? We're going to get 24 for t sub 1. Now that we know that t sub 1 is 24, keep in mind that if we want to find the first three terms, then t sub 2 just means that it's a common ratio of negative half. To get from t sub 1 to t sub 2, you take that value and multiply it by a ratio of negative half, right? So therefore, t sub 2 is going to give us a value of negative 12. T sub 3 is taking that value of negative 12 and, with a common ratio, multiplying it by negative half to get us a value of 6. And then from there, since we have those three values, we want to find, oh, that's it, I guess, just find the first three terms, right? That's about it, okay? So that'll conclude our notes for today. Sorry again for the disruptions, both my son and those texts on Boba Day. But I hope you guys have a good week, and I will see you during the Zoom session. Bye-bye.